Hi. Hey everyone, it's Chaz. I'm back with another video, and this time we are going over LeetCode problem 3, longest substring without repeating characters. This will be our first medium problem on the channel. Problem says, given a string S, find the length of the longest substring without repeating characters. We have an example string here, and our output is 3 because the longest substring with no repeats has a length of 3. So that would be right at the beginning, ABC, but also BCA, CAB, there's another ABC. Since they all have a length of 3, okay, lucky. Since they all have a length of 3, it doesn't change our output. It'll just be 3 regardless. Then another example here is just the same letter over and over again, so it's impossible to get a string longer than 1. And then last example here, our longest substring would be right here in the middle, WKE, which has a length of 3. So we return the number 3, and they make sure to tell us that we need an actual string of consecutive letters. It needs to be a substring, not just a sequence. All right, now let's take a look at the constraints. There is one important thing to look at here, and it's that the length of the string, s.length, is allowed to be 0. So we're going to have to take care of that issue. The method that we're about to use will not be able to handle a string of length 0. So we're going to have to deal with that edge case separately. Speaking of our strategy, we will be using the sliding window strategy. And the way this works is we're going to create 2 pointers. We'll call them left and right. If we have a string here, like example 1 on LeetCode, just for the sake of making things easier to understand, I'm actually going to put the index values of each character right above each character as well. And we're going to put our 2 pointers here on the screen. Left will be blue and right will be green. And then what we're going to do is create a hash set to store the unique characters. So I believe we've worked with a hash map in the past, which stores pairs of values. The keys have to be unique, but the values are allowed to repeat. But in this case, a hash set, it's not pairs of values. We are just storing single values in the hash set, in this case, single characters. But the thing about the set is that no repeats will be allowed. So if I try to add a character to my hash set that's already in the hash set, it's just going to overwrite that character. You won't find 2 of the same character. So let's have a box here on the screen to represent our hash set. Next step, I'm going to check if the character at the right pointer is currently in the hash set. And then that's going to branch off into 2 decisions. So first of all, if it is not in the hash set, we're going to add that character to the hash set and move the right pointer forward. And then if that character is in the hash set, we're actually going to remove the character from the left pointer and then move the left pointer forward. And then our final answer is just going to be the largest window between the left and right pointers. So what we're saying here, since it's a sliding window, the 2 pointers are going to get farther and closer to each other, sort of like a window opening and closing. And at the end of this problem, we should find the largest opening of the window. And the way to calculate the opening of the window would be to just simply find the difference between the right and left pointers. So I'm going to put a box here for right minus left, and we're going to keep track of the maximum difference between the right and the left pointers. So the max of right minus left. So right now it's 0 because the left and right pointers are together. They're both on the same index, 0 minus 0. Now let's go back to step 3. We need to check if the character at the right pointer is in the hash set. So basically we are asking about the green arrow, the right pointer, is A in the hash set? Well, right now there's nothing in the hash set, so the answer is no. So we're going to add that A to the hash set and move the right pointer. And since we move the right pointer, what we're going to notice is anytime we move the right pointer, the window will get larger. So that's the time that we need to check if it is currently the largest opening, or if right minus left is currently at its maximum. So in this case, the right pointer is at index 1, the left pointer is at index 0. 1 minus 0 is 1. Our previous max was 0, so we need to update it to 1. So let's update that. And now we're just going to continue with our little algorithm here. So we're going to check if the right pointer is currently in the hash set. So we're asking, is B in the hash set? The answer is no. So add B to the hash set, move the right pointer, and let's just check our window. It's currently 2 minus 0, so we've reached a new maximum. Let's update the max to 2. Now we ask about the right pointer currently at index 2 with character C. Is C in the hash set? No, it's not. So let's add C to the hash set. And let's move our right pointer again. And because we move the right pointer, index 3 minus index 0, that's 3, so we have a new maximum. Let's update that. And now with our right pointer at index 3, character A, we ask, is A in the hash set? This time, yes, it is. It's already in the hash set. So we're going to remove the character at the left pointer, which in this case also happens to be the letter A. So we will remove the letter A from our hash set. And this time we're going to move the left pointer. Now, anytime we move the left pointer, there's really no reason to check how big the window is, because whenever we move the left pointer, the window will always be getting smaller. So it can't possibly be the new maximum. But now the right pointer is still at index 3, so we need to ask again, is A in the hash set? This time, it's not. So we're going to add the A straight back into the hash set, and then move our right pointer. Since the right pointer moved, we should check our maximum. However, 4 minus 1 is 3, so we don't need to update our max. So now our right pointer is at index 4, and we ask, is B in the hash set? Yes, it is. So we will remove the character at the left pointer at index 1, which in this case is also the letter B. So we will remove the B and then move the left pointer over. So basically, to explain what we're doing, our goal is to get a string of unique characters. So anytime we find a character that's not in the hash set, we're successfully finding a longer string. That's why we move the right pointer, and that's why we make the window larger. However, anytime we find a duplicate, at that point, it doesn't make sense to move the right pointer anymore. We shouldn't be making the window larger. If anything, we should make it smaller until we are down to a string that only contains unique characters again. And that's why we make the window smaller. And since we moved the left pointer, we need to get rid of the character that was at the left pointer since it's no longer part of our string. Therefore, it shouldn't be part of the hash set either. And then we should just make the window smaller until we finally have a string of unique characters again, and then it's okay to make the window larger. Now, the right pointer is still at index 4, so we ask again, is B in the hash set? This time, no, it's not. So let's add B to our hash set, and we're going to move the right pointer. The window did get larger. However, 5 minus 2 is 3. Our maximum was already 3, so we don't need to update it. Now we ask at index 5, is C in the hash set? Yes, it is. So let's remove the character at the left pointer, which in this case is also the letter C. So remove C and move the left pointer. Now our right pointer is still at index 5, so we ask again, is C in the hash set? No, it's not. So let's add C to our hash set and move our right pointer. The window got larger, however, 6 minus 3 is equal to 3, and our max was already 3, so we don't need to update it. Now our right pointer is at index 6, and we ask, is B in the hash set? Yes, it is. So we're going to remove the character at the left pointer, which this time is the letter A. So let's remove the A, and then we'll move the left pointer. The right pointer is still at index 6, so we ask again, is B in the hash set? Yes, it is. So we remove the character at the left pointer. This time it's also the letter B, so remove the B, and then we'll move the left pointer again. Our right pointer is still at index 6, so we ask again, is B in the hash set? This time, no, it's not. So let's add B back into the hash set, and then we'll move our right pointer. The window got larger, however, 7 minus 5 is only 2. That's not greater than 3, so we will leave our max value the way it is. Now our pointer is at index 7, and we ask, is B in the hash set? Yes, it is. So let's remove the character at the left pointer. That's a C. Remove the C, and then move our left pointer. The right pointer is still at index 7, so we ask again, is B in the hash set? Yes, it is. So let's remove the character at the left pointer, which is also a B in this case. Remove the B, and then move our left pointer. Right now our pointers are kind of on top of each other, so I'm just going to separate them a little bit, but they're both still at index 7. And because our right pointer is at index 7, we ask again, is B in the hash set? No, it's not. So we will add B to the hash set, we will move our right pointer, and at this point our right pointer is now outside of the length of the string. So this is where we would stop. However, since the right pointer did move, we do still have to measure the window because the window did just get larger. So we kind of have to pretend that there's an extra index out here, index 8, even though it's not part of the string. However, in this case, 8 minus 7 is 1, and 1 is not greater than 3. So we will just leave the 3 as it is, and that's the value we will return for our longest substring with no repeating characters. All right, so oh, never mind. Hi, Lucky. All right, come on. I tricked him. Well, tricked myself. So some of you may be wondering at this point, what happens when you remove a character from the hash set, but that character is actually still in the string at that moment? So let's take a look at what happens. I'm going to give an example string here. These are going to be my left and right pointers. We'll just put them aside for now. And it's just going to be A, B, C, D, C, E. That's going to be my string. And I'm going to put my hash map right down here. Or rather my hash set, sorry. Right, so I'm going to set up my left and right pointers. They're both pointed at the very first character, the letter A. And we said that if this character that the right pointer is reading, the green one, if that character is not in my hash set, I'm just going to add it to my hash set and move the right pointer. So that letter A, hi Lucky. That letter A goes into the hash set. Yes, that's a letter A. And then I'm going to move my right pointer over to the B. Then I check, is the B in the hash set? No, it's not. Add the B to the hash set, move the right pointer. Then we ask, is the C in the hash set? No, it's not. Add the C. And I'm using alphabet blocks here because I only have one of each letter. So this way, there is no way I could possibly add 2 of the same letter to my hash set. And then, oh, okay. No, right here, baby. Right here. Good boy. Good boy. No, not like that. Nope. Okay, we're good. No! All right, move your feet. I know, you're trying to find a place to sit. All right, come on, we got to move your butt. Your butt's got to go this way. All right, hang on, I have an idea. You want some foods? You want the foods? All right, well, that worked. So where were we? Looks like the C is in the hash set, so we must be here. Now we move the right pointer over, and then we check, is the D in the hash set? No, it's not. Add the D. And of course, this whole time we're measuring the length of this string in order to determine the longest substring. We added the D to the hash set and we moved the right pointer over. Now we ask, is the C in the hash set? Well, yes it is, but we don't remove the C. According to our algorithm, we remove whatever's at the left pointer. So we actually have to remove the A. So you may be thinking, well, now aren't there 2 C's in the hash set? No, because according to our algorithm, we actually don't do anything to our right pointer when we find that character in the hash set. So as of right now, the C that's in the hash set is this one. We haven't actually done anything to this C yet. So let's keep going. We don't want this substring to count because according to our pointers, there are 2 C's, so we don't want that. So once again, we check if this C is in the hash set, or rather if the letter C is in the hash set. And right now the letter C is in the hash set. So we're going to remove the character at the left pointer, remove the B, and move this over. Now we check, is this C in the hash set? Yes, it is. So we remove the C from the left pointer. That C gets removed from the hash set. And now that you move this over, when we check if this C is in the hash set, it's not there. So we can put the C right back in. So we never lose that information because the whole time we're waiting for this left pointer to reach this character. And when it finally reaches the match of that character, we can remove and then put it right back. And then we can continue our algorithm by moving this over. I want to go over the time and space complexity of this problem. Our time complexity is going to be big O of n, where n is the length of the string. And that's because each character in the string will be visited once by the right pointer, and in some cases, even the left pointer will visit it. But either way, it'll come out to a total of 2 spans or 2 runs of the string. So maybe you could say the time complexity is 2n. However, when we are talking about time complexities, we usually just remove the constants, because the main thing we're really concerned with is how does the time complexity increase as the size of the string increases. And in this case, it will still be linear. In other words, if we double the length of the string, the number of operations will also simply double. The space complexity will also be big O of n, where n is the length of the string, and that's because we had to create a hash set to store the characters in our input string. And in a worst case scenario, if every character in the string is unique, then the entire string will end up being stored in the hash set. All right, so we have our explanation. There's only one thing left to do. Hi. You want to do it with me? Let's code some Java. He doesn't like when you pet him right here. See? So we said we were going to deal with an edge case where the length of the string is 0, or even where there is no string, like the string is simply null. And in that case, if the string is null, or if it's just an empty string, the length is 0, we're going to return a value of 0 because the length of that substring would simply be 0. All right, next we're going to create our variables. We need a left pointer and a right pointer, so I just set them both equal to 0, so they will end up starting at the very beginning of the string, at the index 0 of the string. We have a variable that I'm going to name max length. We're going to start that at 0. I need a hash set. The hash set will contain characters. I'm going to just name it set. And so we say hash set character. Character is in angle brackets. Set equals new hash set. Now we have our loop. And this loop will continue as long as the right pointer is less than s.length, the length of the string. And so we have our if statement, and we say if the set contains s.char at right. So hold on, let's work from the inside out. Well, that would be the character at the location of the right pointer. Just like in our example, say the right pointer is currently at the value 1, then we're asking if the character at position 1, which is the letter B, we're asking is B in the hash set. And because I have an exclamation point in front, I'm actually asking, is B not in the hash set? So if B is not in the hash set, then that statement will be true. The set does not contain that character. So if no, add it to the hash set. So there is set.add s.char at right. So add the character that's currently at the right pointer, add it to the set. We also said we would move the right pointer. So there's right plus plus. And because the window gets bigger every time we move the right pointer, we should also do a check if the length right now, but the distance between the left pointer and the right pointer is currently our max. So that's what this one is. And I'm just using a built-in function of Java. You don't need to import anything to make this work. It's just math.max. And then in parentheses, you just give it the values that you want to check. And the variable max length will be assigned to whichever one of those two is currently greater. All right, and then what do we do if that character is in the hash set? Well, that will be our else statement. So in this case, like in the example here I'm showing you, the letter A is in the hash set. So we said we would remove the character at the left pointer. So we have set.remove. What are we removing? s.char at left, the character in string s at the left pointer, and then move the left pointer. So that's left plus plus. And then once the right pointer has moved outside of the string, our loop is complete. And so we simply return the max length. Whatever max length is at that moment, that'll be our final answer. So return max length. All right, so here is our final code. If you want to pause and look through it all, I'm going to hit submit on this. And our runtime of 8 milliseconds looks pretty good. So yeah, that's it. Thank you very much for watching. Oh, I said I would write it down. Hold on. Okay, be sure to like this video, subscribe to the channel, share, and I'm just kidding. There's nothing on this paper. But yeah, thanks for watching. I'll see you next time. Why are you biting me? I'm going to bite you.